Hi guys, I apologize in advance for the environment, maybe a little bit noisy here, but I'll try to continue with our routing protocols. So the last time in the real lecture we covered the RIP protocol, which is one of the distance vector ones, and in this lecture I'll try to go over OSPF and BGP. I'll maybe try to split this lecture in two parts, so kind of smaller versions. So OSPF, so it stands for Open Short Path First, and effectively it is a link state protocol. Like everything that we talked before about link state is kind of applies to OSPF. And as a reminder, the property of the link state protocol is that everybody needs to know the topology of everybody else, or I mean the whole topology in the network. And to do that, effectively every node trying to maintain knowledge of who neighbors are, kind of highlighting by this picture, and then effectively broadcasting this information to everybody in the network. So effectively, if everybody does that, like everybody does that kind of in different ways, everybody will eventually get the knowledge about the topology. So what the protocol essentially defines is a few operations. So one operation is to discover who the neighbors are, and the other operation is kind of the propagation mechanism. There's also operation of how exactly the prefixes are attached into this environment, and we'll talk about this in a few moments. Just to highlight, OSPF is much different from a RIP protocol, and I really suggest you to take a brief look at the RFC, the standard that defines RIP and OSPF, and you will see the difference by at least by the number of pages. As a small exercise, just give me the number of pages in one and the number of pages in the other one. Kind of similar to what I already showed about the RIP. So this is the just highlight of the Wireshark of the OSPF protocol, and one big difference how OSPF is doing compared to the RIP. So OSPF is not built on top of UDP. So if RIP was on top of UDP, they reserved a specific port. In OSPF, they somehow decided to work on top of the IP protocol directly. So they, instead of just using some transport protocol ID, they have this protocol ID 89 to represent OSPF, kind of as working on top. There is one implication of that, and specifically, you can only have one OSPF instance running, because it's kind of you lost the ability to do multiplexing effectively because you don't use UDP, TCP, and using something directly. You can only have one OSPF. If you do something inside OSPF to kind of split in different places, that's a different story. But just to remember this specific thing. And as I said, the specification is much more complex compared to what I already showed with the RIP protocol. Instead of just one header that effectively does everything, with OSPF there is tons of several headers, several messages for the different types of exchanges. And this is just a highlight of what those different messages are. I'm not expecting you to kind of completely remember all those details. Just remember there are different messages. I already highlighted how OSPF works, and kind of the first thing it needs to do is to send so-called the hello message to discover that someone, your neighbor, is alive. So this is slightly different from what you saw in the RIP. In the RIP, we only have one message that acted as hello message, had an announcement of your costs, and everything else was tied to that single message. In here, the hello message is just defining the connectivity. And as soon, I mean, I will probably show on the next slide how fast this hello message being sent out, but as soon you detect the failure, you effectively trigger some kind of link state update. So if I create a new packet saying, oh, I'm connected to this, and kind of this new connectivity, and I'm trying to propagate this information. Again, different from RIP, it's a little bit more harder state. So like in RIP, it's always soft state, and you expect it to send message every, let me know how many seconds. And kind of if you didn't receive within a certain period of time, you declare a failure, and that's how you proceed. In here, you as a person who detected the failure will trigger the error, trigger some update. This will, information will be propagated. Everybody will hopefully receive this information, and new stuff will happen. However, they have this additional backup option, like that mentioned on on the last bullet here. So if everything is fine, you still create a new link state update. Like every 30 minutes, you just kind of saying, "Oh, I'm still here," even though everybody knows that everybody is still alive because no failures were triggered. This is just additional guard mechanism in case there was some sudden disconnection or some kind of very bad thing happened in the network. So the cool feature of OSPF is that each update is being published in so-called LSP, link state packet, and each packet is associated with the router that originated it and a sequence number. And effectively, what's the cool about this is the LSP with the highest sequence number is the one that you're interested in, because the previous LSPs with the smaller sequence number will be representing some state that happened before, and the biggest one is the effectively the current state or estimated current state, and you can kind of ignore this part afterwards. And I will show you in next slide. It has actually have yet another purpose. To have the sequence number in the first place. And finally, there's a few other things, literally small things. For the propagation, so router generates the LSP, and it's been kind of effectively broadcasted and rebroadcasted in the network further and further until either it reaches everybody or TTL becomes zero. Like TTL is part of the IP packet. And after each router receives the update, they will recalculate the topology graph, recalculate the routes, and kind of be done at this point. So for the part of, I didn't mention yet, but it's so-called reliable flooding. So the whole logic for disseminating LSP is everybody effectively rebroadcasting it. But there is one condition, actually two conditions. So one, you receive the LSP, like a router receives LSP from its neighbor, and it will try to broadcast it everywhere except the guy, except the link it just received this LSP from. And it will not do this action if it already received this LSP. And it will kind of how exactly it will know it, because it has its internal database. So effectively, each router for each other part, that's kind of the basics of the OSPF in the first place, because you have to maintain topology, and to maintain topology you have to keep these LSPs. And if you receive a new one, you actually check against it as database, and if you already have something in database with potentially smaller sequence number or smaller sender ID, something like TTL, you just discard this information and don't rebroadcast. So this effectively allows you to reduce number of things that you broadcasting. And as we already discussed, those LSPs are generated either based on some event that you detected that effectively will happen fairly quickly. It's a very, very quick detection of that your neighbor is disconnected or something bad happened, or periodically on very, very long time scale. So if you remember a few slides back, it was 30 minutes. And just to highlight all this propagation, so assuming X generated some new LSPs, so there's some event happen. So what can happen, X will broadcast like flood this LSP to all its neighbors, to A and to C. Effective to the next step, we're going to have that this update got propagated. Both A and C will try, and they detected that it's a new LSP and they didn't have it in its database, so they will decide to rebroadcast it. So A will send it to B and kind of not going to send anything back. C sending to B again, not sending anything back. So the next step, we're going to see B effectively receive the same LSP twice. But the cool feature of kind of remembering that you have the state, it doesn't really matter from whether B received this information from A to C. It's the same information. and it will act on the first one. On the first one, it will send it to D, but when it receives the second one from C or from A, it will simply ignore it. So kind of at that point, everything is fine. And kind of a reasonably simple question to you: how many LSPs message traverse each link in the absence of failures in and out? So try to think of this. So in absence of failures, you remember how often the LSPs are being generated, and they generated individually by every single router in a system, and you can calculate how many things will happen in the network. So give me this answer, and I hope you got some idea of OSPF. So all the routing calculation is using this very simple algorithm that we discussed in one of the previous lectures. But the mechanics are this. There's announcements. There is hello messages to kind of to detect who the people are. There is LSP to actually describe to whom you connected. And the part that I didn't mention, but it's also important, is there is also messages to announce some information attached to you. So besides that you need to declare your neighbors, like connectivity of neighbors, you still need to advertise certain prefixes. So the OSPF is actually pretty cool regarding this part, because it technically allows multiple different protocols to be used. So the topology is independent of what you're announcing. So one thing is just discover how you connect it, and the other one is announce certain prefixes. So here's a random example of like a recent version of OSPF that supports IPv6. It's actually internally using like IPv4 identifiers to identify the routers, but then announcing IPv4 or IPv6 prefixes to inside the network. One thing that you may be able to see on this slide, there is so-called router ID and area ID. So this one is a little bit advanced uses of OSPF. Kind of OSPF in general is for intra-domain routing, meaning it's only for inside the network, where you have, like as a single entity, have the full control. For simple networks, you don't have any kind of area. Everything is one area. You know everything about everything. But if you have a kind of complex network inside your enterprise, you may want to have some form of a hierarchy. That there is a main backbone and there is a little bit secondary networks and so forth. So it's not ideal. So OSPF is not really great regarding this kind of real hierarchy, and it's actually only one level of hierarchy, and it's not really that working well. But it exists there. So if you're interested, you can learn more, like for example on Wikipedia somewhere. And again, compared to RIP, there is some kind of authentication built in as part of the protocol when it was designed. That the example I'm showing here is even for the first specification of OSPF, compared to what we saw in RIP, where there was absolutely nothing regarding authentication. Okay, so that's all I want to say about OSPF. I hope you got some reasonable understanding of what it is, and using small exercises I put in the lecture, you should be able to understand a little bit deeper what exactly is happening.